Hello everyone. In previous lecture already we have started microwave tubes which are classified in two types, that is O type and M type. O type tubes are linear beam tubes like klystron tube and travelling wave tube, and M type tubes are cross-field tubes like magnetron. In this lecture, we are going to study construction and working principle of magnetron. This is the construction of 8-cavity cylindrical magnetron. It is nothing but a diode, usually of cylindrical configuration with a thick cylindrical cathode at the center and a coaxial cylindrical block of copper as an anode. This. In the anode block, there are cuts, a number of holes and slots which acts as a resonant anode cavities. The space between the anode and cathode is the interaction space, and to one of the cavities is connected a coaxial line or waveguide for extracting a microwave power. It is a crossfield device as the electric field between anode and cathode is radial, whereas the magnetic field produced by a permanent magnet is axial. The permanent magnet is placed such that the magnetic lines are parallel to the vertical cathode and perpendicular to the electric field between cathode and anode. These are nothing but the cooling fins. To understand the operation of cavity magnetron, we must first look at how the electrons behave in the presence of closed electric and magnetic field. Depending on the relative strength of the electric and magnetic fields, the electrons emitted from cathode and moving towards the anode will traverse through the interaction space as shown in this figure. In the absence of magnetic field, that is when B equal to 0, the electron travels straight from cathode to anode due to the radial electric field force acting on it, which is indicated in path A. If the magnetic field strength is increased slightly, that is for moderate value of B, it will exert a lateral force bending the path of the electron as shown in path B. The radius of this path depends on the electron velocity and magnetic field strength. That is, radius of the electron is directly proportional to the electron velocity and inversely proportional with the magnetic field strength. If the strength of magnetic field is made sufficiently high so as to prevent the electrons from reaching the anode, which is indicated in path C, then the anode current becomes 0. The magnetic field required to return electrons back to cathode just grazing the surface of the anode is called the critical magnetic field BC or cutoff magnetic field. If the magnetic field is made larger than the critical field, that is if B is greater than BC, then the electron experiences a greater rotational force and may return back to cathode quite faster as shown in path D. All such electrons may cause back heating of the cathode. This can be avoided by switching off the heater supply after commencement of oscillations. In this figure, you can observe if the cathode is biased to a high negative voltage, typically at -10 kV, and resonant cavities blocks in the anode are biased at DC 0 voltage, then there is no magnetic field and electrons travel directly to the anode block in a radial path. Instead of this, if a magnetic field is applied which is perpendicular to the plane of this drawing, then electrons now travel in strongly curved paths and induce an electromagnetic field in the anode block. All the previous explanation is for a static case in the absence of RF field in the cavity of magnetron. Assume that if RF oscillations have been initiated due to some noise transient within the magnetron, then the oscillations will be sustained by device operation. As pointed out earlier, self-consistent oscillations will be obtained if the phase difference between adjacent anode poles is n pi by 4, where n is an integer. If n equal to 4, which results in pi mode of operation, which is shown in this figure. Here, the anode poles are pi radians apart in phase. The dotted electron paths refer to the case of static fields with no RF field. The solid path refer to the electron trajectories in the presence of RF oscillations in the interaction space. The electron A is seen to be slowed down in presence of oscillations, thus transferring energy to the oscillations during its longer journey from cathode to anode. Such electrons which participate in transferring energy to the RF field are called as favored electrons and are responsible for bunching effect. An electron B is accelerated by the RF field and instead of imparting energy to the oscillations, it takes energy from oscillations, resulting in increased velocity. Hence, bends more sharply, spends very little time in the interaction space, and is returned back to the cathode. Such electrons are called as unfavored electrons, which do not participate in the bunching process. Rather, they are harmful because they cause backheating. Similarly, electron C, which is emitted a little later to be in correct position, moves faster and tries to catch up with electron A, and electron emitted at D will slow down to fall back in step with electron A. This results in all favored electrons like A, C, D to form a bunch and are confined to spokes or electron clouds. This process is called as phase focusing effect, corresponding to a bunch of favored electrons around the reference electron A. The spokes so formed in the pi mode rotate with an angular velocity which is corresponding to 2 poles per cycle. The phase focusing effect of these favored electrons imparts enough energy to the RF oscillations so that they are sustained. In this way, the microwave energy is generated in the magnetron.